Action.
Got it. Okay, so let's chit chat about the lab from yesterday. So here's the overriding theme, is that both graphs have to show the same thing happening at the same time, okay? But they're gonna show up differently, all right? So hopefully your position time graph looks something like this, where this is kind of a shallow curve at the beginning, and then that line becomes pretty linear. And then your velocity time graph is going to start at 0, 0, it's going to spike up and then pretty much go horizontal. Typically, that's what it would look like. So the heart and soul of this lab is the question where I say, hey, describe how the shape of the graph, what you can figure out, okay? And so you want to talk about what the shape of the graph is, okay? That's the whole point of the question. So you need to say something like on the position time graph, there's two distinct kind of things happening on this position time graph. So you would say, okay, at the beginning, the line is curved. And this is like, it's just a logic problem. And you go, okay, let me think. Slope represents velocity. So if the slope is changing, therefore the velocity is changing. And if the velocity is changing, it's a two-trick pony. The velocity is either getting faster or the velocity is getting slower. That's it. So as soon as you see a curved line on a position time graph, that's it. It's either speeding up or it's slowing down. The line is becoming more steep, the line is becoming more shallow. Okay? So that's what you need to address. So you would say something like, I look at my position time graph, I see a curved line at the beginning, that's becoming steeper. Oh, that indicates that it's speeding up. That's all you have to say, okay? And then you say, wow, then that line becomes pretty straight sloping. Because it's a straight sloping line, that indicates that my velocity is constant. Okay? That's all you have to say. You don't have to write you're not describing a doctoral, your doctoral thesis, anything like this. Just talk about that. And then you're going to do the same thing here. So if this velocity is increasing here, which it is, how does that show up on the velocity time graph? The line is rising rapidly. That indicates that it's speeding up. So that's what you want to address. Okay? Now, make sure on your position time graph that you have a couple of things going on. You should have a horizontal line somewhere that indicates that average velocity. Take your total displacement, divide it by 12. That's typically around 2 to 3 centimeters per interval. Okay, that's an ish, but it's typically something around that.
Shouldn't that one be on velocity?
Huh?
That's on the long graph, right? Yeah, shouldn't that one be on velocity?
Yeah, my bad.
Freaked me out there a little bit. I
Oh,
was
back
like,
off.
oh no.
Okay. That should be here. This should be the straight sloping line. So you should have a diagonal line that shows that average velocity, and then you should have a horizontal line on your velocity time graph. Okay? Cool with that. On your velocity time graph, I should also see like some arrows indicating that this thing is speeding up. If you're slowed down at all, you're going to have a down arrow. Okay, now remember, and this is the most common mistake that happens, and that was the whole point of those questions on the back side of the lab. If you have a velocity time graph, and let's say that it does something like this, okay? And there is 0 meters per second. If this is your velocity time graph, does that thing ever change direction?
No.
No, you shake your head emphatically no. Why?
Because it doesn't stop all the way and then go, and the velocity doesn't change sign.
Yeah. All I'm doing is I'm moving with some positive velocity. I'm speeding up, okay? So here I am, I'm walking along, right? I'm speeding up, slowing down, speeding up, slowing down. Why do I never change direction? What does that line not do?
Doesn't pass through the x-axis.
Doesn't go through 0 meters per second. Okay? Now, do not look at this graph and go, oh, you don't change direction because you don't go past the reference point. Okay? This is not the reference point. This is just 0 meters per second. I have no idea where I'm at. All I know is that I have a positive velocity. I might be walking this direction, it doesn't matter. I don't know where I'm at. So don't look at this and go, oh, you don't go past the reference point. Not what this is about. Okay? Now, does my acceleration change sign? All day. I go from positive acceleration to negative acceleration. But I don't change direction because I don't cross through 0 meters per second. Okay? So just because, and I'm going to tell you this, I'm going to tell you this straight up. I'm going to ask you this question. It's going to be a true or false question. I'm going to say true or false. If the slope of a velocity time graph changes sign, you change the direction. I promise you, I'm going to give you that question on the test, straight up, just like that. So let's settle this. True or false? If the slope of a velocity time graph changes sign, you change direction.
False.
Absolutely false. Okay? What would I have to say to make that statement true? It has to cross through 0 meters per second. Okay? So just because your slope of your velocity time graph changes sign does not mean that you change direction. Okay? All right. Anything else you want on the lab? Hints?
On number 1, which graph did you want it from? The dependent, was it
You
the
can just do
velocity?
the position time graph. That's fine.
Oh, is it okay if it's the velocity time?
That's fine.
Okay.
Either one. Either one is fine. All right. Eli.
On like number 10 and 11, is it okay if I had it like not stop immediately because the battery's died?
As long as I just see that it's there. The steepness doesn't matter.
Okay.
As long as the shape is there.
Okay.
Because you don't know what the time scale is.
Mm-hmm.
So as long as I get the shape, that's the main thing.
Okay.
Okay? All right. Anything else? Once, twice, 2.5. So stay correct. I hate it when kids beat me to the soul. It's okay. So staple the graph to the back and put that handed in.
Can we make this a straight line then?
Wow. But no, I'm just gonna
You're so sweet, Kaylee.
put your graph at the very bottom and your word at
Hashtag
the
with
very
this.
top.
X-axis might be better than all of my work.
I'll bring it. Oh, I'm just trying to push
Wow, you sent me colors. You guys know that Trevor said there's something spicy again? I'm quite excited.
Alright, what are we looking for?
Really? Okay, I'm gonna go get a pumpkin.
Yeah, I have some carbs
I saw that.
pretty busting. I did some roller. You pulled it up and she carried it.
Yeah, I tried it. It was good.
Oh, sorry.
I'm gonna try it. I'm gonna why an LR beefing?
Your friends are smart, so your
What happened?
She's mad because I didn't open the pictures.
It's because of the lunch. You also ate her something that you told her that you brought in. Yeah.
That was me.
Oh. I don't have my glasses on, so all I hear is like the voice from that part of the room.
He's just watching me walk.
That answers the question.
Sit down. You get front row.
Is it really?
Ah, what the heck?
It's pretty good. Preston, you can bring your What was the score?
10-0.
When's the mercy rule?
Halftime.
Let's be 10-0 by.
You guys lost?
No, like you're not. I can think of meaner people.
Gracie?
Yeah, Gracie's like not mean at all. I've never heard her say a bad thing about someone.
Okay, so,
Did you say Gracie's not mean? Are you delusional?
Why are you guys being so mean to Gracie? It's all Gracie's mean to me.
Gracie's really mean to me.
Yes, she is.
Gracie's really mean to me.
Yeah.
Yeah,
You should see her during volleyball. No, Gracie's nice.
No.
I find that hard.
When have I ever said anything
Okay.
to anybody? Exactly.
You always say
So-
mean stuff.
Today we're going to take this whole idea of position time graphs to like literally another dimension. So we're going to revisit the trip to Kansas City, okay? So it's after school today, but you want to go to Kansas City, and you're on a time crunch, okay? You don't have time to drive. So you call up the old man and you say, hey, Pops, need to get to Kansas City, need to hit the Cheesecake Factory. Mind if I borrow the corporate jet? Dad says, fine. Got nothing going, you can do that. So you're gonna fly to Kansas City, it's gonna take you an hour to get to Kansas City. You're gonna be in Kansas City, and then you're gonna be back, okay? 3 hours round trip. So I would argue that that could be the position time graph for the trip to Kansas City. How could that be the position time graph for the trip to Kansas City?
Yeah.
Position in the air. Okay? So if that's the case, what we're keeping track of is
Elevation.
elevation. So what we're keeping track of here is our vertical position as a function of time. Now, this is what you have to watch, because yesterday on the lab that you all did with the constant velocity device, you had a position time graph that looked like this. True? But was the cart actually climbing up a hill? No. What was the cart doing? It was speeding up,
from it.
and it was moving away from a reference point, right? So, if you think about it, what happened yesterday is like you were looking down, and you saw the cart start at a certain point relative to that spark timer. You turned it on, and that thing was going away from the reference point. So we had a graph that started there, and then was going away from the reference point, but because the graph was climbing, that doesn't mean that the cart itself was climbing. It just meant that it was going away. So like you were looking down and you were seeing it go in this direction. So this is what you have to keep track of. Which axis of motion are you talking about? Are you talking about the vertical motion, or are you talking about horizontal motion? So if you're flying to Kansas City and you're using the ground as the reference point, then you're saying, hey, we're going to start at the reference point, we're going to cruise up to cruising altitude, we're going to stay there, boom, we're going to land, we're going to stay there for an hour, boom, we're going to come back, boom, come back down, okay? So here's the difference. If it's vertical position versus time, if that graph is going up, that means that object is physically going up in the air, okay? Because it's going away from that horizon, and you're going away from that. Going parallel, hey, you're staying up there, you're coming back down. So this one actually matches what's happening physically. The bottom graph, just because it slopes up like that, doesn't mean, oh, I'm going up a hill. So that's why you have to keep track of what you're talking about. Now, let's say that we're still going to do that graph. We're going to do horizontal position versus time. Okay, excuse me, vertical position versus time. Vertical position versus time, relative to the horizon. But Dad says, hey, you know, planes being used, you can't take the plane, but if you have the time, you can go ahead and drive. So if you were, keeping in mind that we're in Kansas, what would your vertical position versus time graph look like if you drove to Kansas City and back?
It'd be flat.
Out the
Yeah.
driveway.
Basically, it'd be like, Flint Hills. Flint Hills.
You know what I heard is that Kansas is flatter than a pancake.
Oh, it is. That is a true story.
Really?
Yeah, they actually, the person did a comparison of Kansas on the same scale as the surface of a pancake, and Kansas is flatter than a pancake.
That's funny.
No, it's a true story. Seriously, if you look at a pancake, it has like those, all those little air pockets and things in it. So if you take Kansas on the same scale as a pancake, we are flatter than a pancake. It's like, you were really hard up for something to do. Now, let's say that we do want to keep track of horizontal position versus time, okay? So if we were to drive to Kansas City, okay? If we were to drive to Kansas City on a position time graph and keeping track of horizontal position versus time, what would that graph look like? Just roughly, what would it look like?
It'd look like one hill.
We're going to go to Kansas City and then we're going to come back.
One.
Just go like this, and then like this, and then like this.
So
Trap
we're
is
going to
one.
drive to Kansas City, right?
Means you're
And then we're going to
neutralized.
stay in Kansas City for a little bit, and then we're going to
Drive back.
come back, right? So let's say that's driving. So there's 3 hours, there's 4 hours, there's 7 hours. So that's driving, okay? Now, what would that look like if you were to fly to Kansas City? So what would the horizontal position time graph look like if you were still flying to Kansas City? And you're keeping track of where the plane is relative to Wichita.
Similar.
It'd be a smaller range.
Same general shape,
Yeah.
but much steeper. Why? It's faster. So if you were to fly to Kansas City, it'd be something like this. Okay? Same general shape, much steeper. But Dad says, plane's out of commission. You had too many speeding tickets. We're not going to let you drive. But we got a horse. Okay, I'm up for the challenge. So if you were to ride a horse to Kansas City, what would that graph look like?
A lot longer.
Yeah, it'd be like, okay. Could you get there?
Yeah.
Take a while, right? You'd get there. But that's going to get real, real flat. So here's my point, is that when you look at position time graphs, you have to keep track of which axis you're talking about. Are you talking about vertical versus time, or are you talking about horizontal versus time? Now, shut that camera down, and then know the concept of a roller coaster. So what provides the thrill of a roller coaster? Constant velocity or accelerated motion? Acceleration motion, right? Constant velocity roller coasters don't sell very well. Okay, it's like, what do? I go in a straight line at a constant speed. Now, if that's like faster than the speed of sound, legitimately, that might be fine, okay? But if you're just going in a straight line, pretty boring. So the whole function of a roller coaster is to do 3 things to your velocity vector. Make it bigger, make it smaller, and change the direction. That's the thrill of a roller coaster. And the faster that rate of your velocity vector changes, the more you accelerate, the more thrill that has. So what we're going to do is we're going to start with this, and we're just going to look at this segment from here to like here. So start this up here, boom. So we got it from here to here. Now we want to describe that motion. So what's the first thing that we have to decide? No. Let's say something else.
Doing it on horizontal.
Vertical or horizontal? Which one do you want to do first?
Horizontal.
Vertical? Okay. So we're going to do the vertical. What do you want? Now we can talk about the reference point. Do you want the reference point to be the ground, or where do you start?
Ground.
Okay. So here's our motion, right? Ground is the reference point. We're starting here, going like that. So from here to here, what would that position time on the vertical axis look like? So we're already starting up, right? Okay, so we're going to start there. Then what's it going to do? We go down, okay?
0.
You're gonna go up,
Then we go up,
then you come back down,
then we come back down,
then you kind of flatten, yeah.
up a little bit,
Yeah.
okay? But that doesn't show a loop. How?
With the second, no, the hill thing
What about the hill thing? How does the hill thing show a loop?
goes off and comes down.
Okay, now, why couldn't we draw the position time graph where something like, where it like doubles back?
That is not allowed in graph.
Yeah, go back time, cool trick. Okay? Now, for those of you that are hardcore math people, because it's hardcore, if something's a function, you have what's called the vertical axis test. What does that mean? Bingo. You
X can't have
cross
more
one
than
two
2,
points.
whatever.
Because if you draw a position time graph like this, you're saying at this point in time, you're at 3 different locations at the same time, which would be cool, okay? Don't get me wrong, right? Like, where are you at? Oh, 3 different places, okay? So even though it does go through a loop, right? What's that beeping noise?
It's a timer.
Yeah.
Oh my god.
Should we be worried?
Oh my god, that's crazy.
My switch is done. Oh, man, my loading. Okay. We'll deal with that later. Okay, so, now, here's the question. Let's stop. So here's the question. If this is all you saw, does that necessarily mean that there's a loop?
No.
What could happen?
Just to help.
Yeah, we could actually have a hill, right? It could go down the hill, up the hill, over the hill, down the hill. So since this is vertical versus time, you could actually build the roller coaster like this. So here's my point. If this is all you see, you can't necessarily tell that there's a loop, okay? All you know is that it starts up high, falls, rises, falls, goes up a little bit. That's all you have. You can't tell that there's a loop because you can build the roller coaster that looks like this. Now, at how many direction changes are there? How many?
No, none.
There's no direction change.
There is 1, 2.
1.
Those?
Those?
1, wait.
3.
Yeah, there's 2. Wait, no, 3.
Uno,
3.
dos, tres.
There's 3.
Tres?
Oh, I need to put this on.
Why tres?
Because that very ending thing, it switches.
So, is everybody cool that we have a direction change here?
Yes.
Yes. Physically, where is the roller coaster at that point? The bottom, right? Because it's going down and then it's going to start to go back up. Positive velocity to negative velocity, right? Now, if you're a math nerd, this is a relative minimum. Now, we'll talk about tangent lines more in just a second. The other thing that can happen is if you can draw a tangent line, and tangent lines touch a circle at only one point, if you can draw a tangent line that's horizontal, your velocity at that point is going to be what? 0. And you only draw tangent lines when the velocity is changing. So if you can draw a horizontal tangent line, your velocity is 0, and you're going to change direction. Can you do the same thing up here?
Yeah.
Yes. So this is a relative maximum. Down here you're going to have a relative minimum. Let's hear it from math nerds. Here's the application. This is the only time you're ever going to use maximum and minimums outside of a math class, I swear to God. This is the only time it's going to happen. Enjoy, embrace this moment. Okay, so I have 3 direction changes. Got it? Fantastic. Okay, now let's talk about what's going to happen horizontally versus time. So we're going to get this, refresh our memory, we got that action going. So what do you want the reference point to be? Now we're keeping track of horizontal
Right there.
this time.
Where it started.
Okay, so this is going to be where we're going to start. So what's that going to look like?
It's
Go
gonna.
far, then come back.
So if this is the reference point, are we going to start? I lost my marker. Oh, we'll change
It's
it
gonna have a mini
up.
hill.
Aqua blue. Okay,
Start at 0.
so this is horizontal position versus time. Okay? Where's this one going to start?
The bar 0, 0.
At the reference point, right? Because we defined that point as being our reference point. Then what's it going to do?
Up. This way.
It's going to go up. Then what?
Then go down.
Go down.
A little bit.
Now we'll go all the way back to 0.
No,
No, why not?
because it's only a little
Yeah, it doesn't
circle.
go all the way back to reference points. Here to come back a little bit, then what's it going to do?
Curve back up.
Could go back up.
Past it.
So, how many direction changes does this one have?
2.
2. Now, if I have this is all I see. Can I have this action going without a loop?
Yes.
Yeah.
I mean, depends on what you've defined as a loop.
Yes, because you can go out.
Yeah, you can go like,
I could go like a big S curve,
yeah.
right?
Yeah.
I could go out, hit an S curve, come back like this, and go like that. Because I could be flat and have this happen, right? Now, here's what you have to remember about this. When you're on this graph, imagine that this is the leap of faith that you have to have. Imagine that you're looking down on top. And the only thing that you can keep track of is what's happening on the horizontal motion. So if I look down on top, I'm in a hot air balloon. I'm looking down. So all I can tell is that this thing is going away from the reference point, and then it comes back to the reference point, and then it goes away from the reference point again. That's all I can tell, okay? I can't tell what's happening vertically. All I can tell is that I'm going away, coming back. Is there a way I can do this same thing without using an S curve?
Yeah.
What?
You go, like, it can be a roller coaster that goes down and then goes forward, but then it makes you stop and come back and then go forward.
Okay, I could physically go forward, stop, come back for a little bit, and then go forward again. It would be the exact same thing.
What if you know those like little boat things, the Viking boats, and they go, yeah. It's like a pendulum, you know?
Yeah.
Because if you start at that place and then you,
up.
yeah, okay.
But yeah, that's what you're talking about.
Whoa.
Okay, small detail. Okay. A roundabout.
Oh, that's a good one.
Ooh. What if I did a horizontal loop?
Whoa.
That got a whoa from Topher. Okay, whoa. So, imagine the roller coaster comes down and we do a loop like this. Would that produce that curve?
Yes.
Oh, it could
Okay.
be one of those. It could be one of those spinny ones, and the person could be the position, and so it spins at that point, and then the person
Catches you and like spins you out?
Yeah.
Yeah? Now, however, we do have a loop. So, where is, on this point, right here, where is the roller coaster, or where is the cart on the roller coaster at that top relative maximum? Is it at the bottom, or is it at the side? Why?
Because that's when it's farthest away from the reference point.
Yeah, because if you look at this coming in, I've lost my roller coaster. Oh, there it is. So we're going away from the reference point, right? So it's at this point when the direction changes. This is when it's going to start going back to the reference point. When it's here, what's going to happen?
set your minimum.
That's going to be that other relative minimum, because then it's going to start going away from the reference point again. So what you got to be able to do is transpose both ideas at the same time. You sit here and go, okay, I have a vertical change in direction. At the same time, I'm going to have a horizontal change in direction. The only way that can happen is if you have a vertical loop. Now, if all I did, let's say I had that going in, I would go down, and let's say I would have a horizontal loop, and then go back out. What would my vertical position time graph look like?
It would not go up.
Yeah, it would go down and then basically hit Kansas. Okay? Here, we're in Colorado. So if you superimpose these, oh, we've got a vertical loop. Got it? Good? Grand? Back we go. I guarantee you, I do know I am not going to do
I'm just confused. Never mind. Did you get the Lululemon bag?
Okay.
I think you have the pink one. You have two?
I got nothing.
Oh my god.
Okay. Now, so let's dig deep into your memories of the days when you were in geometry. And no, I'm not going to make you do proofs. I know. I will not make you do proofs. But what do you know about tangent lines? How many points does a tangent line touch a curve? One. So, what you have to do is kind of imagine that here's the radius of that circle, and it's going to touch that circle at one point, and that's going to be at a right angle to your radius line. Over here, here's your radius, that's a right angle, right? So, imagine this. You have a circle. Your tangent lines can touch at one point, and it's going to make a line at a right angle to the radius at that point. Everybody cool with that? Okay. Now, just keep that in mind. Just park that away. We'll get back to it. Now, let's say that I'm going to give you a position time graph. And it's going to be something like this. So there's 4 seconds, and there's 12 meters. Okay, so there's 2 seconds, and there's 6 meters. Okay? Could you find the slope of that line?
Yes.
What would the value, what's the slope of that line?
3 meters per second.
3 meters per second, right? Because if I take 12 divided by 4, if I take 6 and divide it by 2, it doesn't make any difference. Slope of this line is 3 meters per second. Now, here's what's important. Does it make any difference which point in time I pick?
Not if they're the same.
Not if that slope is the same. At any given point in time, 2 seconds, pi seconds, whatever, it doesn't make any difference. As long as you have a straight sloping line on a position time graph, at every point in that interval, the velocity is the same because it's not accelerating. Okay? So, can you even draw a tangent line to a straight line?
No.
No. So here's the deal. If you have a straight sloping line on a position time graph, that means that you have constant velocity. That means that at any point on there, the velocity is going to be the same. It doesn't make any difference which point you pick. It's all going to be the same. Okay? However, we always don't travel at constant velocities. Sometimes we accelerate. Now, if you have a position time graph that looks like this, okay? And let's say that this is 3 seconds, okay? And let's say that's 4 meters, and let's say this is, okay? Now, let's say that I want to know how fast you are going at 3 seconds. Okay? I want to know how fast you're going at 3 seconds. Here's the problem. we're trying to find the slope of a curved line. Okay? Can't do it. Okay? So when you are accelerating, and how do you know you're accelerating if you look at the position time graph? Yeah, it's a curved line. Because if it's a straight sloping line, you are at constant velocity. So you have accelerated motion, and what you're trying to find is instantaneous velocity. I will have to tell you like a specific point in time. I will say, hey, how fast is Maggie going at exactly 3 seconds? Okay? Now, the problem is it's a curved line. I can't find the slope of a curved line. So this is what you're going to do. You are going to take a ruler, okay? And this is what I wish I could draw on this thing. But imagine, and this is like a leap of faith, okay? So you just have to imagine that you have, this is part of a circle. So imagine that this whole thing is part of one big circle, okay? And you want to draw a tangent line at that 3 second mark. So you got to imagine that your radius line is here, and you're going to come in here and you're going to take that ruler and you're going to draw that line where it touches that curve at exactly 1 point. Okay? So you're going to come in here and you're going to draw this line. Is that my ice cream? Okay. What?
Sounds kind of like the buzzer, like in a basketball game.
Huh? Okay.
What? Stop.
So, now, so this is 3 seconds and 4 meters. So, I know that point. 3 seconds and 4 meters. But to find this, and what we're searching for is what's known as instantaneous velocity. Okay? The only time you draw tangent lines is when you have accelerated motion, which means you have a curved line, and you're trying to find the velocity at a particular point in time. So, how many points do you need to find the slope of a line? 2, right? Now, I can use 3 seconds and 4 meters as one of my points. But what I cannot do is I just can't take 4 meters and divide that by 3 seconds and say, oh, that's my slope, okay? Because otherwise you're just using 1 point to define the slope of a line. Because if you just use that point, then you would say no matter what line crosses through there, it's always going to have the same slope, which clearly isn't true. You can use this as 1 point. So let's say you come out here and you find another point, let's say that's at, I don't know, 5 seconds. You pick another point on there and you go, okay, maybe that's 5 seconds and, I don't know, 9 meters. Now I can find the slope of the line because now I have 2 points. Now here's the problem, okay? Taylor draws her tangent line. Jack draws his tangent line. Because you're eyeballing it, there might be a little bit of difference in those. So the only way that I can judge this is by seeing your work. Now, if you eventually do calculus, calculus comes to the rescue. Calculus takes the chance out of this. Calculus, if you know the equation that generates the line, you take the derivative of it. The derivative of it gives you the slope of the tangent line, and then you get your instantaneous velocity that way. Okay? But since most of you haven't done calculus, we're going to do this the graphic way. Okay? So, if I wanted the velocity at this point in time up here, I draw a tangent line like this. I draw a tangent line. So what has to happen is that you have to generate the curve, and then I'm going to pick a point and say, find the velocity at a particular point in time. Got it? Good? Okay, so stop that. Because that's how I roll. Okay. Now, so let me explain what you're going to do. You're going to end up drawing 3 graphs, okay? So if you want, you can take a sheet of graph paper and go like, are we going? Mm-hmm. Okay, you can do like 1, 2, 3. If you want to do like one on the front, one on the back, another one kill trees, that's cool. It's up to you. You can do like halves, whatever you want to do. But let me kind of take you through each graph. So on number 1, you're going to plot a position time for movement along the ground. Okay? So notice in this you have a column of time. You have horizontal position, which is where you're going this way. And then you have vertical position, which is where you're at in the vertical direction, oddly enough. So your first graph, you're going to start off, and you got to go all the way through like 24 seconds. So you can go from 0 out to 24. So at time 0, you're at 0. At 1 second, you're still at 0. At 2 seconds, you're at 1. Okay? And so what you should see when you get done, not to ruin the surprise, but it's going to look something like this. Okay, so when you get done, this is roughly what your first graph is going to look like. Then I'm going to say, describe the shape of the curve. This does not have to be a 5-paragraph essay. I don't want to know how it makes you feel when you look at the curve, okay? Not what I'm about, all right? Really not a warm and fuzzy kind of guy, shocking as that may be to some of you. But what does the curve look like? Again, it's just like, if you're a math nerd, you can go, oh, it's like a cube function. If you're a biology nerd, you go, oh, it kind of looks like snake. Okay, strike. Then we're going to say, is the velocity constant in the horizontal direction? Okay, look at the graph. Does the slope change? Yes or no? Does the velocity change? Yes or no? There you go. Now, number 3 is the most critical one. So you're going to go to the 8-second mark. And trust me on this one, your 8-second mark is going to be about right here. And you're going to come in here and you are going to draw a tangent line that touches that curve at one point at exactly on that 8-second mark. So you're going to come up here, you're going to find your 8-second mark. You're going to find out where it touches that curve, and then you're going to have to just eyeball that tangent line. So imagine that you have a radius like this, and that's going to make a right angle to that. Now, everybody's is going to be a little bit different. If there's a graph that you draw big, do the first one, okay? Because you're going to have to draw a whole bunch of tangent lines on this particular graph. So if there's one that you do kind of go big on the first one. Then you're going to go to the 12-second mark. The 12-second mark, trust me, is going to put you somewhere over here. So that's going to be that second tangent line. So that's going to be something like this. Now, just stop at this point. When you draw this 8-second tangent line right here, is that velocity going to be a positive or negative number? Positive. Sloping line goes like that. Positive. So you know your velocity has to be a positive number. Now, at the 12-second mark, it's coming down like that. Maggie, positive or negative slope? Negative. Okay? I like that kind of a southern drawl. Negative. Listen, okay? I like my graphs. so this was, what do you think about that all day? So, now, does the slope of your tangent lines change sign?
Yeah.
Yes. Yeah. Why didn't you hesitate? Yes, it changes sign. So what did the cart do?
Change direction.
Change direction. Oh. When do you think it changed direction? Before or after the 8-second mark?
After.
So at some point you're going to come up here and guess what? I'm going to ask you to draw a tangent line to that relative maximum. What's the slope of that tangent line going to be?
0.
0. Don't make that complicated. Okay. Then you got some questions to ask them about that. When you get to question number 5, imagine that you are in a balloon and you are looking down on the roller coaster. And all you can describe is the horizontal motion. Okay? I don't want up, down, left, right. All you can tell is what's happening in a horizontal motion. That's all you can describe. When you get to question number 6, here's going to be the second graph. You're going to plot vertical motion versus time. Let me give you a hint. The roller coaster is already at the top of the hill. Okay? So the second graph is going to start up there at 11 meters, okay? You're gonna plot those points, okay? This one, you don't have to draw any tangent lines for. You just have to plot the points. Now, when you get to question number 8, okay, I want you to have this visual. The roller coaster is back there at the other end of the room. I'm seeing the roller coaster come towards me. The only thing I want you to describe is what's happening, well, about what I can see vertically, okay? So here's how this is going to start. You're going to say, oh, I'm going to see the roller coaster at the top of the hill. Okay, that's how everybody's going to start. Ah, what's the roller coaster do? Oh, it's going to fall. Probably it's going to go back up again, okay? So basically that's what you're going to describe on number 8. Start off, I'm looking at the roller coaster, it's coming towards me, and all I can see is vertical motion, okay? That's all I can see. When you get to number 9, let me explain exactly what I want done on number 9. You're going to draw a third graph. You're going to put horizontal position here. You're going to put vertical position here. This one has nothing to do with time. Okay, this is the only one that does not involve time. What you're going to do is you're going to plot the shape of the roller coaster. Now, so that you get a true image of the roller coaster. I don't care what your scale is, and I tell you this in the instructions. I don't care what you choose your scale to be. And this is the only one that this has to happen on. It doesn't happen on the first 2, but it has to happen on this third one. Whatever you choose your scale to be in one direction has to be the same scale that you use in the other direction. So if you're going to let one grid be 3 meters going horizontally, you have to let one grid be 3 meters going vertically, okay? If you want it to be 2 and 2, 5 and 5, I don't care, okay? They just have to be the same. Otherwise, you get a distorted view of the roller coaster. So if your vertical axis is bigger than your horizontal axis, then you get like an egg-shaped roller coaster, okay? If your horizontal is bigger, then you get like the egg laying on its side. So it doesn't have to be that way on the time ones, but it has to be on the ones where you're plotting positions. So same scale. I don't care what the scale is. It just has to be the same going on both axes. Okay? Now, here's the heart and soul of this whole thing. And that's going to be question number 11. Okay? So, you're going to go between 7 and 15 seconds. Okay? Not 7 and 15 meters. Between 7 and 15 seconds. So, you're going to come to this graph of vertical motion versus time. And you're going to look at what's happening between 7 and 15 seconds. You're going to look at that graph during that interval. Is it going up? Is it going down? Is it going forward? Is it going backwards? What's it doing? So you're going to say between 7 and 15 seconds, horizontally, this is what the roller coaster was doing. And then you're going to go to the next one, to the vertical versus time, and you're going to say, hey, between 7 and 15 seconds, this is what's happening. It's going up and it's coming back down. Or it's just going up. Or maybe it's just coming back down. I don't know. So you're going to reference, you're going to say between 7 and 15 seconds, horizontally, this is happening. Between 7 and 15 seconds, vertically, this is happening. And then the summation is that then you're going to go to the roller coaster itself and you're going to go, okay, since this is happening vertically, this is what's happening horizontally, this is where I'm at on the roller coaster itself. Let me give you a hint, there's a loop on the roller coaster. So are you on the top half of the loop? Are you on the bottom half of the loop? Are you completely inside the loop? Okay? Then you're going to do the same thing between 17 and 24 seconds. Horizontally, what's happening between 17 and 24 seconds? Vertically, what's happening between 17 and 24 seconds? And then, where are you at on the roller coaster itself? Okay? Good? Got it? Great. Any questions? Make it happen.